wish Jurek special birthday. Jurek studied almost simultaneously with me, so when he started studying, I think I was after my first or second year here. Also, but of course, there's like 2 years entrance is a big gap, so our paths started intersecting perhaps only around our master thesis, and so which means that we've known each other for about 35 years or something like that. So, so happy birthday, Jurek, and so the aim of my talk is to present you the following theorem. So the energy momentum vector of asymptotically hyperbolic manifolds is time-like future pointing unless you're in hyperbolic space. So this is a positive energy theorem for such manifolds unless hyperbolic space. So unless hyperbolic space. So I'm not sure that everyone is familiar here with these various objects, so I'm going to define them. This sounds like a theorem in mathematics, but it has to do with physics. First of all, it's a statement about spacetimes with negative lambda. So this ties it to physics now because asymptotic hyperbolic manifolds arise as initial data sets for spacetime with negative cosmological constant, with one catch here that it should be time symmetric. So it's not a completely general statement, and a general statement still awaits. So second thing would be, so what's the physical example? Of course, if you think about space-time with negative lambda, then the first thing to think about is the ADS anti-de Sitter space-time, where the metric is of this form. Which mainly, well, most of people here know. And here is a metric on a sphere. And this is important in my talk because there are manifolds called locally asymptotic hyperbolic, which also have very similar properties to this one. And but then this metric here would not be a metric on a sphere, but on some other compact manifold. So the function here is in the case of anti-de Sitter space is b square root of 1 plus r squared. And the main point of this talk is that this theorem is true regardless of the dimensions here. The statement was known before if you assume that you have a spin structure. So it was known for spin manifolds.
I think when you say hyperbolic manifolds, you're also putting some conditional extrinsic curvature, or is it symmetric?
Time symmetric. So no extrinsic curvature if you want to think in terms of physics, right? But so to tie this with physics, of course, I need in the theorem that the scalar curvatures are okay. So we have this asymptotic hyperbolic manifold. I haven't told you what it is yet. So it will be asymptotically hyperbolic if it has a region so that G asymptotes to G0 in the asymptotic region. In a rate which is irrelevant here. Just sufficiently fast so that you can define the energy, and of course the requirement which I should have said immediately is that the scalar curvature of this metric should be larger or equal than R of G0, which, if you normalize things correctly, is minus n minus 1, I think, where n is the dimension. So this is the setup. You have manifolds so that the metric asymptotes the hyperbolic metric. Well, okay, I'm a little.
Confusion between G naught, is this space? Yeah.
So let me just write this is G naught. This is space-time metric. This is the space metric. Okay, so we're getting there. Good. And so now, so this metric is actually the metric on hyperbolic space, and we're looking at metrics so that G asymptotes this metric asymptotically at a sufficiently fast rate so that mass is defined.
And n is 3 or 4?
Say it again?
N is 3 or 4 in classical case?
And in the classical case, n would be 3. This is the space dimension.
The space dimension.
Good, so let's go back again. Energy momentum asymptotic hyperbolic manifolds. So at least we know what an asymptotic hyperbolic manifold is, at least loosely, and in any dimension is time-like future pointing, unless this is hyperbolic space, and then if R of G is larger than minus n and minus 1. So if you want to tie this to the constraint equations in GR, they will tell you that R of G, if you have an initial data set mgk, where this is the metric, this is the initial, this is the extrinsic curvature, then there will be energy density. There will be a term which is coming from the cosmological constant. There will be a term coming from this tensor, which is k squared minus raised k squared. So this condition that R of G is larger than this constant, well, this is coming from the cosmological constant. When the constant is negative, this means, because R is larger than this means that the energy density will be positive if these terms are not here. So this is the time symmetric case where these terms are not here. R larger than R of G naught means that energy density is positive. You could, of course, have still this contribution here, which gives a positive term, which still fit in this framework, but I don't want to start discussing this, so let's just, for simplicity, assume that this is 0 if you want to talk about physics or initial data sets, or if you want to take just about the Riemannian problem, you have a scalar curvature which is larger than the negative constant, and you have a statement about mass. So I told you that the result was now for spin manifolds. Well, every three-dimensional manifold is spin. So if n is equal to 3, the problem is solved by Wheaton some 40 years ago almost. So the new thing here is that this works in any dimensions without the spin assumption. So what is the energy momentum? So there are so many people here who worked on this and know very well what it is, that it's embarrassing to tell you what it is, and I'm not going to give you even attempt to sketch the derivation. So there's many derivations both from the mathematical side or from the physical side, or Hamiltonian analysis or symplectic analysis, which give you expressions of what should be the energy of initial data set. So mgk, in particular, if this is 0, what should be the energy here? In a setting where this initial data set comes with a space-time which has an asymptotic killing vector. Okay, so you think of space-times plus a metric which goes to 1. So this is the space-time metric, right? And this one has a translational killing vector. Then you can write down a formula for what the energy in such a space-time should be. And this formula, well, it will obviously depend upon the geometry, and maybe not unsurprisingly will depend upon this function v here, because this is actually the norm of the killing vector, right? If you're thinking about energy, you're thinking about things associated with a time translation, and so the killing vector here is v over dt, and v squared would be just the norm of this killing vector. And so there are various ways of writing this, but so let me call this energy momentum vector, which depends upon a function v. This is an integral with a constant, which I don't care about. It's a constant, and now we can start arguing what it should be in various dimensions. So maybe a dimension-dependent constant, and you take a limit as r goes to infinity. You integrate on large spheres, so this is r, so you go with r to infinity, and you integrate the trace-free part of the Ricci tensor of this three-dimensional geometry. Right? So you have this function v, which is associated with the killing vector, and to this function you associate a limiting integral, which involves the gradient of this function v and the Ricci tensor of the space geometry. So this formula is essentially...
Excuse me, in 4 dimensions, it corresponds to the electric part of the vial.
This is Riemannian. This is not the space-time.
Yeah, the Riemannian part, this is what you have written, is electric part of the vial tensor as the initial data.
So what you're saying that this is nothing else than a formula that Abai and Romano wrote in a paper many years ago, and indeed it is, right? Yeah. So written in this form, or almost in this form, explicitly in this form, I know it from a paper by Helsley, but it goes back to a formula that Abai wrote using the space-time violence. This is essentially what people call the Abbott-Giza energy. The Abbott-Giza energy looks completely different, but they have to integrate by parts a few times to get this formula. If you are in a asymptotically flat case, you have essentially the same formula for the ADM energy, not exactly this one, but something very similar in terms of the Ricci tensor of the initial data. Again, take the standard formula for the ADM, integrate by parts, and you're going to get something which looks like that. So this is, you can think of this as a direct generalization of the ADM energy to the case where you have space-times with a negative cosmological constant, right? Because it's not, if you have a negative cosmological constant, there is no way this can be asymptotically flat. So if you want to talk about energy, you need something else. This is the formula. So now, well, energy momentum vector. How come this is a vector? Well, that's the easiest way to understand it is as follows. This metric is just the hyperbolic space, And hyperbolic space has a lot of symmetries. So you can act with a symmetry on this part of the metric. You're not going to change it. But if you act with a symmetry on this part of the metric, this function will change. And the fact, so therefore, you don't have only one function, which is possible, because if you start acting by isometries on your metric, you're going to get a whole family of these. Right? How many you will get? Well, as many as the dimension of the group of symmetries of hyperbolic space. So if you are a physicist, you know that the symmetries of hyperbolic space is the same as the Lorentz group. If you're not, you don't know this, but this is irrelevant for this talk. You don't need to know this fact that this is the same as the Lorentz group. But indeed, it is the Lorentz group. And the way to see this is that the hyperbolic space sits in Minkowski spacetime as a hyperboloid. Right? So if you, and the hyperboloid is invariant of the Lorentz group. So if you make a Lorentz isometry, you're going to map this to itself. And that the fact that this is one-to-one needs a proof, but this is what it is. So you have these hyperbolic isometries which act on this function and produce a family of how many? Well, n plus 1 functions. So there is a function of V0, which is the one I wrote out there. So put this one here. So V0 is actually the same as this one, but there are several ones which appear very simple, much simpler than this one. So if you think of this as these coordinates coming from a spherical coordinates in a Euclidean space, then this would be just this coordinate here. And then V is a linear combination of these functions here. V mu, let's see, maybe I should put it like that. V is a constant, alpha mu, V mu, okay? So any function which appears here by acting with the hyperbolic, with the group of isometric hyperbolic space on this one, is a linear combination of these. Well, that's a calculation you have to do. And then you can say that P mu is, so alpha mu are constants. P mu would be just P of these basis functions V mu. And so now you have n plus 1 numbers, because you have n of those, one here. So you have, you can say it's a vector. And so this is my energy moment. And now there's a fact that P mu transforms as a Lorentz vector under isometries of the background. The simplest proof would be, well, what else? What other possibilities would there be? But if you're not convinced with this one, then this is, you just do the calculation and this is what you find. So now the statement is, you take a asymptotic hyperbolic manifold. So this is a metric which asymptotically goes to this one. You assume that it corresponds to physical initial data, and so positive energy, and this corresponds to the condition that the scalar curvature of the metric should be larger than a constant, which is 2 lambda, and you can always rescale by a constant your initial data set so that this constant takes this value. So this is a scaling condition which is irrelevant, but just normalizes things. So then you can calculate these n plus 1 numbers, and these n plus 1 numbers form a Lorentz vector. This Lorentz vector is time-like future pointing, and unless we are in hyperbolic space, in which case it's 0. Good. So, as I said, this was already known for spin manifolds. Well, this was known for spin manifolds, both in the hyperbolic case and asymptotically flat case. Now, if I go back a little bit to the asymptotically flat case, where there is a relevant notion, then the spin case was settled 38 years ago. But in 2016, Lockham showed that in the asymptotically flat case, asymptotically flat, then you have a notion of energy momentum vector. So now, so you have positivity, so P mu time-like future if the dominant energy condition is satisfied in any dimension. Now, this is a theorem which has not been published. It's only available in the archive. There can always be surprises whether the proof is complete or not. So there is a closely related paper by Shon and Yao, which do the same for time symmetric initial data, right? So Kij equals 0. So an alternative proof in the case Kij equals 0. Perhaps a little simpler to understand than this one. Both are milestones of mathematical general relativity. Extremely sophisticated, beautiful arguments. So this is a asymptotically flat case. Until these two papers, this was not known in all dimensions, right? So these are the first papers which settle the problem asymptotically flat in all dimensions, without any conditions like spin or some other dimensional condition. And one reason why I'm mentioning them is not only that they're beautiful and important, but I will use them in my proof of positivity, right? So this is to be assumed, the result is assumed, or a tool to prove this theorem. Good. So let me just then now tell you all the steps of the proof. So steps of the of my theorem. So let me call this theorem A. So that well, first, n equals 3 is spin, right? So I don't have to do, so nothing to do. So I can just go to any larger than 4.
Piotr, can I just ask, is it obvious that your integral above, the one rho of v, that it's convergent in any dimension under the assumptions that you've made?
Well, I didn't tell you how far, what are the conditions. I mean, you just assume positivity. No chance, right? But so there are some decay conditions which you have to impose to make sure that these intervals converge. And I can write them down for you if you want to now. But so you have to put a rate on how fast this approaches.
But in the space-time language, it is asymptotic matter of Penrose, so you can have the boundary. Then is convergence.
So if you have a smooth conformal boundary, then this will converge.
In any dimension?
In any dimension, if you assume that the metric on the conformal boundary is a round sphere, which is enforced by this asymptotics. But you need much less. So actually, it's important that you need less when you do proofs, because you do various constructions which you don't have the full control if you would have in this case. Good. So how do I go? First, n I don't need to do, so n larger than 4. Then let's see, what would be the next step? Probably so this is step number 1, would be to show that P mu cannot be time-like bus pointing. And this is not obvious, and requires some work, and maybe I tell you something about it. No, I will not tell you anything about it because of time. So this is a kind of boring part of the proof. 2 is the interesting part, as far as I'm concerned, is that P mu cannot be space-like. So if you draw the light cone, by part 1 we know that it cannot be here. By part 2, no. Time goes this way. So it cannot be here. By part 2 it cannot be here. So it could be cannot be space-like or null bus pointing. So it cannot be here, but it cannot be on the cone itself. So it will be on this cone or on the boundary. And the third part is that it cannot be null future pointing. So the least, I think all 3 parts are interesting. The third part is not is something that was proved not by me but by let's see. So this is Lan Huang. I think it's you, Martin, and a third author. I apologize for the author who is not in the audience, but if you were, I just forgot his name. So, Chinese name. So, what they do is they show that if 1 and 2 is true, then 3 is true. So they have a very pretty argument which shows that this borderline case cannot arise if you know the previous ones. Number 2 is a joint work with Erwan Delay. And this is the thing I want to talk about now, because I think it's good. And this goes as follows. So this uses gluing at infinity. And there are two kinds of gluing involved. The first one is the following. Suppose that you have a asymptotic hyperbolic metric. It was already mentioned by Abai that these things are closely related to spacetimes which can be conformally compactified. So this is, you can think of this as a compact manifold. Maybe there's some topology inside. But it has a boundary, a conformal boundary at infinity, and the conformal boundary is sphere. So you have this metric here. Then you can make a deformation and suppose that this works for initial data set, but just in this case that we're interested in, scalar curvature satisfies the bound. Then you can construct a new manifold which looks exactly the same as it was looking before, but in this there is a region near infinity. If you may do some colored chalk, where here the metric is exactly hyperbolic. This is a very weird fact, which goes back to a beautiful construction by Carlotto and Schoen, to show you that you can switch off gravitation on the level of initial data by gluing constructions. So their theorem was, suppose you have asymptotically flat initial data, then you can construct a new initial data set so that to the left of this plane z equals 0, the metric is exactly Minkowskian, well, actually flat at the Euclidean at the level of initial data set. And to the, well, there's an interface, and at the right to this interface, the initial data are exactly the same as you had before. Right? So you start with some initial data, you do something terrible to them, and you end up with a new initial data set which satisfies all your positivity conditions, everything you wanted, where gravitation has been completely switched off to the left of this plane. This is exactly what we're doing here. We're switching off gravitation or geometry, making it trivial in a, so this is the boundary at infinity, right? So this is an infinity, the sphere of infinity. So there is a neighborhood on the sphere of infinity, say the North Pole. Around this North Pole, we get the metric is exactly hyperbolic in a space. So this is the first step of the gluing. It requires a bit of work. And why is it interesting? Well, now the result is going to be a contradiction argument. So assume you have a space like P mu. Then, well, the direction of this P mu gives you a preferred direction on your boundary at infinity. I'm going to choose this so that it's well, along the axis of P mu. And it's probably so that P mu is pointing backwards. Okay, so if you want to think in terms of Lorentz vectors, this north pole of the sphere of infinity corresponds to the direction, if we're in 2 dimensions, so this is 2-dimensional Minkowski, that this vector P mu is pointing in this direction. Okay? So this is your space-like energy momentum vector, if it exists. Now, the next step is to understand what happens with this setup if you start making conformal transformations of hyperbolic space. And what could it be? Well, the conformal transformations make out of the Lorentz group, and these things, the sphere of infinity, you can think of this as this set of null directions. So if you make this conformal transformation, it's the same as making a Lorentz transformation. This Lorentz transformation, which will shrink this sphere of infinity, well, will move the sphere to infinity to anything you want. So if you started with this region here, and you start making a Lorentz transformation, you can make it to a larger region, or an even larger region, or even go further than half of the space. So by making conformal transformations, you can map this little region here to anything you want, as big as you want on this, by making Lorentz transformation. Well, what is going to, we know that the Lorentz transformations associated with this act as Lorentz transformation on this. So if I keep boosting in this direction, what's going to happen with this vector? Well, if you are at rest, these are the space and time directions. And if I keep boosting, these things go nearer and nearer to the light cone. This means that this vector is going to go nearer and nearer the past light cone. And therefore, if I boost far enough, it's going to have a negative component of mass. And if I keep boosting, it's going to be more and more negative because I'm just squeezed near this light cone. Okay, so if I make these Lorentz transformations, I'm going to get an initial data set which has still a space-like vector, because this Lorentz transformation I can do anything, and I can have that P0 is negative. So what do I do now? Well, I take 2 copies of this thing. So I have one which is here, where I have hyperbolic space here. I take this, I rotate it so that this region becomes this region. And this is, again, a Lorentz transformation, conformal transformatory. It just is going to move this vector here. So I have a vector P0 and P, which is coming from here. And after rotation, so that I can make a rotation so that this one has P0 minus P. And now the metric is exactly hyperbolic in this region. So I can identify these 2 initial data sets near the totally geodesic surface which cuts in half. And I'm going to get a new initial data set which looks like non-trivial here, non-trivial here. Good. And actually exactly hyperbolic here, coming from these 2 pieces here. And I'm adding, so now the question is, what is the angular momentum of this thing? The space-time, the energy momentum vector. Well, what else could it be? It's the sum. Again, this is something which you should prove. Actually, it's really trivial to prove from this formula, because the energy momentum is as the integral over these 3 regions here, and this region gives you no contribution because the metric is exactly hyperbolic here. So it's going to be the energy momentum from this one, energy from this one. So these 2 cancel out if you add them. This has energy momentum P0, P plus P0 minus P. And this was negative. This cancels out. So you get an initial data set with fast pointing time-like energy momentum, but this is not possible by 1. So this is the proof, and if you're interested, the details are in papers on that.
So, we are assuming part 2, I mean, this whole construction assumed that the PV is space-like typically when you do this. But what happened if it was null? Because it's also null and fast pointing, because null vectors will remain null vectors.
It's right, so if it's null plus pointing, I already have P0 negative, so I don't need to do anything. So I have immediately, so I just do these things. But
it remains null, it doesn't change.
No, so this works the same, right? So the important thing is that you want to have, if you assume that you have P0 negative, you do this construction, you end up with something which is past pointing timer, right? So if you started with no past pointing, then you'll be adding this vector to this vector, which is this vector. You still need to do this boosting and gluing and stuff like that, but
I guess, and one needs to prove that last result which says that the
yeah, so I mean, once you know how it works, these things are so obvious, what else could it be, right? So that you still need to work a bit to prove that these things work. But,
Let us thank Piotr again.